and welcome to the video demonstration. Today I am going to walk you through a project focused on one of the most critical challenges in modern artificial intelligence, algorithmic fairness in computer vision. We have built, audited, and mitigated demographic bias in a one-to-one facial verification system. In this video, I will explain the societal impact of biometric bias, walk you through the code base, and demonstrate how we achieved fairness without sacrificing overall accuracy. First, let's understand the application. Facial verification is a one to one matching process. It answers a specific question. Are these two images of the same person? This is the technology used to unlock your smartphones, authenticate bank transactions, or verify identity at border controls. It is fundamentally different from facial identification, which is a one to many looking up asking, who's this person in the large database? Because one to one verification is used for high stakes authentication and access control, security and fairness are paramount. If the system fails to match you, you are logged out of the service. This is a false rejection. If the system matches you with someone else, it commits a security breach. This is a false accept. So, why do we need fairness audits? Biometric systems do not perform equally for everyone. Landmark studies such as MIT's Gender Shades project reveal that commercial facial recognition system perform significantly less accurately for women, younger and older individuals, and people with dark skin tones. These perform gaps leads to a real world harm such as false arrest, systematic profiling, or denial of basic services. In response, global regulatory framework like the EU AI Act and NYC Local Law 144 are actively mandating rigorous disaggregated fairness audits before AI systems can be deployed in a regulated sectors. In this project, we step into the role of a responsible AI engineer to conduct a multi-axis fairness audit on a deep learning model, expose its demographic disparities and expose its demographic disparities and implement a mitigation strategy to balance those disparities. Now let's dive into the code base. To ensure reproducibility, the entire pipeline is containerized using Docker and Docker Compose. Here is a project root. We have our Docker Compose.yml. It defines a single service ML pipeline which builds our application. We have included a health check that verifies the Python executable and critical libraries like PyTorch. Next, let's open the Docker file. It starts from a lightweight Python 3.10 Slime image, installs the necessary Mesa.gl and system dependencies required for OpenCV headless and runs pip install with the default timeout configuration to prevent the network timeout during package installation. In Docker ignore, we explicitly ignore the data, artifacts, and results directories. This optimizes artifacts and results directories. This optimizes the Docker build process, preventing gigabytes of data files from being transferred to a Docker. Let's inspect how the dataset is prepared. We are using the UTK face dataset, which contains face images labeled with age, gender, ethnicity in their files. In the file dataloader.py, we pass these file names using a regular expression. We map the gender code 0 for male, 1 for female, and bin the age values into four categories: 0 to 19, 20 to 39, 40 to 59, and 60 plus. Because UTK face provides ethnicity labels, we map them as a proxy skin type. White is mapped as light, black is mapped as dark, and Asians and Indian and other ethnicities are mapped to medium. This creates a multi-axis subgroup label for each image, such as female 60 plus dark, etc. In gets data split function, we perform a stratified split using a scikit-learn train test split. We allocate 70% to training, 15% to validation, and 15% to held out audit set. Stratifying on the subgroup label ensures that even the rare demographic subgroups are represented proportionally across all the splits. Now let's look at the model architecture in the model.python. We use a pre-trained ResNet-18 model as a feature extractor. We stripe the final fully connected classification layer and replace it with a custom projection head. This projection head consists of a linear layer, batch normalization, a ReLU activation function, and a final linear projection mapping raw features to a 128 dimensional embedded space. In the forward pass, we apply L2 normalization to the embeddings. This normalization ensures that the Euclidean distance between the two embedding maps directly to their cosine similarities. Below, the get similarity function computes the cosine similarity between the patches of embeddings simply by calculating the dot product, which is extremely fast and computationally efficient. In train.python, we implement the training loop. Standard cross entropy classification loss is not suitable for verification because we want to learn similarity rather than discrete classes. Therefore, we train using a triple margin loss. For each patch, the data loader generates a triplets, an anchor image, a positive image, and a negative image. The loss function pushes positive and pair embeddings closer together and pushes negative pair embeddings apart by a margin of zero point 0.2. The model parameters are optimized using Adam. Now let's examine the audit logic, which is the core part of a fairness verification. To evaluate the model, we first extract the base and augmented embeddings for the entire audit set. Then, for each of the 24 subgroups, we construct a positive and negative pairs. Positive pairs are generated by matching an image-based embedding with its augmented embedding. Negative pairs are generated by matching different individuals with the same subgroup. The function calculate far FRR takes these positive and negative similarity scores and evaluates them against a decision threshold. We count how many positive pairs fall below the threshold and how many negative pairs meet or exceed the threshold. They run fairness audit function This function loops over all subgroups and compiling a disaggregated report of FAR and FRR alongside overall system averages. Let's review the mitigation strategy. In the initial audit, a single global threshold is used for all groups. This creates a severe bias. Subgroups that creates a response represents poorly suffer from very high false reject rates. To mitigate this, we implement post-processing threshold calibration. In calibrate subgroup threshold, we evaluate similarity scores on the validation sets for each subgroup individually. We run a grid search to find the group specific threshold that minimizes the differences between FAR and FRR, known as equal error rate point. During the mitigation audit, when comparing a pair of images from a specific subgroup, we apply the subgroup calibrated threshold instead of the global one. This mathematically equalizes the error rates, ensuring the system is equally fair and secure for all demographic categories. Finally, let's look at the main.py, which is orchestration. This entire pipeline, when executed, handles the dataset loading, saves the demographic configurations, trains the model, saves the weights, runs the baseline audit, perform the bias analysis, calibrates validation thresholds, reaudits the mitigated models, and compile the final PDF memorandum using FPDF2. You can see the entire structure, like the main part of the code written inside the main.py. Demographic.json contains our programmatic demographic specifications. Initial audit.json logs the baseline bias. Analysis.json identifies the largest disparity pairing. You can see like female 0 to 19 dark versus female 20 to 39 light, which had an FRR display of 25%. Mitigation audit shows the calibrated results where the worst group FRR cut off to 12, like 12.5, achieving error parity. The overall metrics.json shows that overall accuracy actually improved from 90.24 to 90.43 due to group optimization boundaries, artifact or model.pt. Uh, these are 45 MB trained by PyTorch weights. To wrap up, this project successfully demonstrates the end-to-end process of auditing and mitigating bias in deep learning system by applying post-processing threshold calibration, which significantly reduce the false reject rate disparity for marginalized groups while maintaining and even slightly improving the overall accuracy of the system. However, as documented, like remaining ethnic risks such as proxy limitations and domain shifts under poor lighting mean the system is only conditionally approved for low risk scenarios and not for unsupervised high stakes environment like retail loss prevention. Here is the environment setup. Thank you for watching this demonstration. All the source code and Docker environments and audit reports are fully committed. You can check this in my GitHub repository. Thank you so much for watching.